Hey folks, listen to another lecture on flippin' physics. All right, so this is where you learn the content at home, but then you come to class a little bit prepared to actually do problems with me. Saves a little bit of time if you do that this way, where you do what we've always should have done. Read the book at home, learn the content, and then come to class ready to try it and master it with my help. All right, so today what we're going to do is do graphing motion. Graphing motion, this is a little bit of introduction to graphs. So let's start with the first one. How about V equals 0? What would the graphs look like if you have V equals 0? We're going to have three graphs. We're going to have displacement versus time. We're going to have velocity versus time. And then we're going to have the other graph, acceleration versus time. So those are the three graphs we're going to talk about. Okay? So I want you to graph all three of these guys. What would the line or what would the data look like if you had velocity equals 0? The thing's just sitting there, parked in a parking lot. What does these three graphs look like? Real stupid, they'll do it. So what I want you to do is pause the video and then see what it looks like. All right, hopefully you paused the video and you didn't just sit here watching and getting entertained by me. That doesn't work. All research has shown if you didn't pause the video and you're just watching me, then you're watching me get really good at it. Okay, so here goes. This is what I hope you have on your paper for displacement versus time. Let's say it was 5 meters away from the origin. There it is. It's 5 meters away from the origin, and it's still staying 5 meters away from the origin. At all times, 5 meters away from the origin. So therefore, what do you think the velocity is? And the answer is it's 0 the whole time. So I don't know if you can see that from where you are, but I just kind of tried to draw a green line right there at the velocity equals 0. And of course, it's not moving, so the acceleration is also smack dab on the 0 line. That's got to be the most boring three graphs you ever did see. So this would be the motion of a car sitting there with an initial displacement of 5 meters, and it ain't moving. And it's still not moving. And every time you look, it's not moving. So there you go. Those are the three graphs for that one. Well, let's try the next one. Let's try to have it so that you have the displacement versus time graph, the velocity versus time graph, and the acceleration versus time graph for, let's say, a new motion. Okay, how about this one? Velocity constant, 20 meters per second. Okay? 20 meters per second equals V average, because V average is equal to V instantaneous. It's always 20 meters per second. Let's say it still started at the origin. And I mean, not at the origin. Let's say it was started at 5 meters away like it did before. Okay? So I want you to graph those three. Would you please pause the video and put the lines or whatever on these three graphs that tell the story of something 5 meters away from the origin at t equals 0, but then it's moving at a constant 20 meters per second every second. Even at 0 time, it was going 20 meters per second. All right? Do that now. Pause the video. All right. Hopefully we're back. If we're not back, then you guys aren't getting what you should get out of this. What does this graph look like? Hopefully the first graph looks like a straight line that's starting at 5 meters per second, 5 meters for the initial x, but then it keeps changing by 20 every second. Every second it went 20 meters per second. I'm sorry, it went 20 meters farther down the road. So after 1 second, it's 25 meters down the road, and after 2 seconds, it's saying, what equation am I thinking of in my mind? I'm thinking x final equals x initial plus v times t, because it's really v average in that equation. So we're looking at 5 plus 20t. Okay, and every second it goes 20 meters more than before. 20 meters more before. The cool thing about this, if you find the slope of this line, the slope of this line equals displacement over time. Change in position over change in time is known as velocity. If it's a straight line, that average velocity is the same as the instantaneous velocity, and the slope of this line would be 20 meters per second. Get it? Okay. Hopefully, on the next one, you have this. A flat line at 20 meters per second all the time. 20 meters per second all the time. And then this area under here would be 20 times the time. That would give you the change in displacement. If you already know that you started with 5, you could figure out the change in displacement, x final minus x initial. This would be x initial plus this area under the curve. Okay, so this area under the curve is 20 times the time. You tell me how long, I'll tell you how far away the thing is going. Isn't that kind of cool? Now the slope of this line is the acceleration. And the acceleration in this case is 0 because I said it goes at a constant 20 meters per second. So the slope of this line is acceleration, okay? And it's 0. In this particular case, the thing is 0, okay? What's the last graph look like? What's the last graph look like? Still boring. It's still an acceleration of 0 the whole time because we did not accelerate throughout the time interval that we used, okay? All right, so hopefully that got you into a place you kind of understood things. How about if we do this over again, but this time let's do the same 3 graphs. That's, again, displacement versus time, velocity versus time, and acceleration versus time. But you probably can guess what I want you to do this time. Now, A is constant. The acceleration is constant. Okay, and the acceleration is a constant, let's say, just for fun, because we've been talking about things, 4 meters per second squared is A. Okay? We'll say that the initial speed equals 0 and x initial was 5 meters. So it starts at 5 meters away from the origin, but it's not moving in the beginning, and therefore the acceleration is a constant 4 meters per second squared, but you could be not moving and have a constant acceleration. You should know that, okay? So pause the video, see if you can graph those 3. Tell the story in those graphs of this scenario. Pause the video and try that now. All right, we're back. Boy, I hope we're back, man. That would be awesome if we were, and I'm hoping you take advantage of this. So over here, you start at 5 meters, but then the original slope is 0 because the slope of this line is velocity, and the slope is 0, so you should be seeing what we call a parabola. And you should understand it's a parabola because displacement was equal to 1/2 at squared, and that's a parabolic function between x and t. Okay? The slope of this line, the slope of that line is still the velocity, but this time the velocity is changing. All right? What's the instantaneous velocity at t equals 0? And the answer is 0. The tangent line gives you the instantaneous velocity. Later on, this velocity is not 0. This velocity is some number bigger than 0. And then later, the velocity is even greater. The slope of that line, the slope of that tangent line, is even more steep than the previous, which is definitely more steep than the 0 time. Isn't that kind of cool? Okay? Now, if you made a line from here to here, and you found the slope of that line, that would not be the instantaneous velocity. This would be the average velocity between 0 and whatever this time was. So we'll say this is T2 and T1. This is T2 minus T1, x2 minus x1. The slope of that line is the average between 0 and the final time. I want you to notice something really cool about the t squared thing. This only works if it's t squared. Only works if it's t squared. But do you see the slope of this instantaneous velocity right here? It seems to be parallel to this line. And if those two are parallel, then it's actually going the average. So if the average is, I don't know, 4 miles per hour, then it's actually going 4 miles per hour at this time here. At this time t, it's actually going 4 miles per hour because the average. Just want you to notice that, because when you do your lab number 3, you're going to use that as a, what I call the Hortense cheating method, but it's actually the mean value theorem. The average between here and here is the instantaneous at the mid-time. That's a real cool thing to write down about 12 times right now that you're watching this. The mid-time instant velocity is equal to the average. So the average between 0 time and, let's say, 4 seconds, the average, whatever that comes out to be, 12 miles per hour or whatever, happens to be the instant speed at 2 seconds. All right, we'll talk about that again. Maybe I'll make a whole another video just for the Hortense cheating method. Okay? All right, if you did your job, hopefully, then this graph here ends up being a straight line. So a parabola in blue ends up being the straight line in the green. The green is the velocity, and the velocity here is not constant. The velocity here is changing. Velocity is changing. The velocity is changing. It's increasing by, I'll be 4 meters every second. So the slope of this line is A. And so the slope of this line is 4 meters per second, or 4 meters per second squared. Okay? And there, it's beautiful, because the slope gives you the velocity, and the area under the curve would give you how far the person went, which ends up being 1/2 AT squared, or V average times time. So you end up with X delta equals V average times time. What's V average? Well, if this is V final, V average is half of that. So 1/2 V final times t ends up being 1/2 base times height. You're finding the area of a triangle. It really does work. Okay? And the last graph, hopefully you have 4 meters per second all the way across, and you got it, if I drew it right, flat line straight across. That was a really bad flat line. I meant to try to make it as horizontal as possible, so I'll do my best. Okay? That's not much better. All right, so 4 meters per second every second. Every second it's changing by force, but the acceleration is the change. The acceleration is a constant 4 meters per second per second. Every second it's changing by 4 meters per second. Remember, acceleration is not how fast you're going, it's how fast you're changing how fast you're going. This was changing by 4 meters per second every second. That means the velocity is changing, but the acceleration is a constant. Okay? All right. We could try one that's a little bit weird, because you guys are ready for that. If you can do displacement versus time, and velocity versus time, and acceleration versus time. But this time, let's say the acceleration is changing. We have a delta A over a delta T. Okay? That instantaneous one would be dA dt, and that would be the instantaneous jerk. Believe it or not, jerk is how you feel in the elevator and how you feel if you ever drove in a car that's a manual transmission with my mom, because my mom never got the hang of that clutch thing. So she would make you jump and you get nauseous in your mind, because you would end up not being able to hold your lunch down when she was driving a car. All right, so what does that look like if the change in acceleration over change in time was 2 meters per seconds cubed? That means every second the acceleration changes by 2 meters per second every second. So what would be a good scenario for a constant jerk? A constant jerk. What would be a good scenario of that? How about a rocket taking off? If a rocket takes off, it has a constant thrust. So the force on the rocket is constant, but the mass of this rocket is decreasing. You have a decreasing mass. You have a change in mass. So if the mass gets smaller, but you're still pushing the same, then the acceleration increases because the mass decreases, but you're still pushing the rocket with the same amount of force. So if F was constant but you lost mass, you would actually have an increase in acceleration. Rockets do that all the time. You have acceleration coming off the launching pad of maybe something like 0.45 meters per second squared when the rocket, space shuttle used to take off at an instantaneous acceleration of 0.45 meters per second squared when it started taking off. But after about 2 minutes into the flight, the thing was already going at 2 Gs, which is affectionately known as another way of saying 19.6 meters per second squared. If you go a little bit more into the flight, man, those guys were experiencing 3 Gs, 3.5 Gs. I think you can experience somewhere around 6 to 9 Gs, depending on how you feel, which is more close to about 60 meters per second squared. Some people would pass out at that. Amusement park rides, there's one near my house called Darien Lake that actually has this innocent looking ride called the Silver Bullet, and that spins you around in a circle with these little things hanging, and you're like living inside this little bullet, and they're all spinning around on this thing, and it actually like bows you right out, and that thing experiences 3.5 Gs, and there's a lot of people that get sick and dizzy with 3.5 Gs. Those fighter pilots sometimes can teach themselves how to survive up to 6 to 8 Gs without passing out. They also have suits that squeeze them, and so pushes the blood back into their brain so they don't pass out. It's really kind of cool. All right, so I've been stalling. What I want you to do is pause the video and see if you can take a really good hypothesis, real good guess on what these 3 graphs look like for a constant change in acceleration, a jerk, constant jerk. The acceleration is changing by 2 meters per second every second. We can say it starts from rest, and we can say that it started at x initial is 5 meters and v initial is still 0, but now the acceleration is not constant, the acceleration is changing. So try that one. Pause the video and give it a shot. Okay, we're back. So hopefully you got this. This thing is x is proportional to t cubed, right? It's t cubed. So this thing is like a really crazy thing. It just jumps up like crazy. I should have started at 5. Let me see if I can erase that. And start up here at 5. There. So it's really a jumping thing. It's like a parabola, but it really jumps up there. That would make this guy the parabola. Okay? So the velocity starts from rest, but the acceleration at t equals 0 is still 2. So it doesn't exactly start flatlining. It starts at an angle and then does a parabola. Okay? And then this dude starts at an instantaneous acceleration of 2 and goes like that. Okay? So the acceleration at t equals 0 might not be 0. I didn't specify if the acceleration was 0 at 0, but let's say the acceleration wasn't 0. Let's say it's 2 meters per second squared right at t equals 0. And that means the slope of this line, is 2 meters per second. All right? So this line is a nice constant line. And the slope of that line would be the jerk. And in this particular case, I said the jerk was 2 meters per second cubed. So that means every second, the acceleration increases by 2 meters per second every second. And we ended up with an equation with a t cubed in it. Okay? I mean, really, you could actually write this equation down that x final equals x initial plus v initial times time plus 1/2 a t squared plus maybe like 1/6 a t cubed, something like that. All right? So it's like you actually have, not t, but jerk, sorry, jerk cubed, 1/2, 1/6 jerk t cubed or something like that. So some constant times the jerk, which is a constant, times t cubed. If you took the derivative of this 3 times, you'd end up back to finding out what the jerk was. Okay? So if you see this kind of graphing, then you know there's a t cubed involved. If you see a flat line on the last graph like we did on the previous page, then you'll see that if it's flat-lined over here, like this was flat-lined, then you know there's a t squared involved. It's only during this crazy stuff. If you see not a flat line on this last one, if this last one's not flat, then you got a jerk. You have a changing acceleration, okay? So hopefully that was a good introduction to graphs, and that really helped you out like crazy.